Okay, hello. We are doing atomic structure today for Edexcel Chemistry and Combined Science Chemistry. There are going to be some high-level topics in this video today, so if you're doing the foundation course, you can ignore it when this higher box comes up on the screen. Otherwise, if you're doing higher-level chemistry or combined science chemistry, this whole video is relevant to you. By the end of this video, you will know the structure of an atom and its subatomic particles, be able to find the number of protons, electrons, or neutrons in an atom, know what an isotope is, and be able to calculate relative atomic mass. Here is a copy of the specification. If you want to go ahead and read that, pause it now. How the atomic model changed over time. So in 1803, John Dalton published The Atomic Theory, which suggested that atoms are solid, indivisible spheres, and each element had its own type of atom. 100 years later, in 1897, J.J. Thomson published his theory that suggested that atoms are positive spheres with electrons embedded inside. We call this the plum pudding model. This is one to remember. You can, to an extent, ignore John Dalton's, but J.J. Thomson's plum pudding model is quite key. I find it slightly easier to think of it as a chocolate chip cookie. I've tried to do that kind of imitation there. If you think of the cookie itself as a positively charged dough and the little chocolate chips as negatively charged little bits inside, so that the whole atom itself is not charged at all, or neutral, is a better way of putting that. That is the best way to think of that model. Later in 1911, Ernest Rutherford published his theory, which suggests that an atom is mostly empty space with a small, dense nucleus inside, and electrons, which are negative particles, orbiting around this small, dense nucleus. So this nucleus is the orange thing with the plus, and the electrons being the blue minuses. He found this from doing a gold leaf test. So essentially you get something that is really thin and unreactive. Gold is a good example. You can use stuff like, you can think of it like aluminium, just take aluminium foil, really thin and unreactive, and blast some particles through it, and you'll find that some of the particles get through, which suggests that atoms aren't fully whole, and in his theory he suggests that they are mostly empty and they only have the small little dense positive nucleus in the middle and a bunch of negative particles spinning around or orbiting around. 2 years later, Niels Bohr refined or perfected this theory, which he suggests that there are levels, there are fixed energy levels where these negative particles, I call them electrons, but you can think of them as negative particles. As you can see, the first orbit, and then the second and the third orbit, and they don't all orbit in one big ring. There are multiple different orbit levels. Now let's look at Bohr's structure in a little more detail. In the center, we have these blue and purple circles, which we call the nucleus. So it's this big clump, which is positively charged, very positively charged. These positive purple circles are protons. A great way to remember that they are positively charged is P. P for proton, proton P. Nice and easy to remember. The blue circles are neutrons. Think of them as neutral, no charge. If you're driving a car and you go into neutral, the car does nothing. It's not braking, it's not reversing, it's not parked, you're neutral, the car continues as is. And then your electrons are your negative. There's no real trick to remember in those. You just remember the other two and process of elimination, or over time you remember electrons are your negative particles. And they're in the rings as Niels Bohr described, with the lower level electrons. For example, these two here are in this lower ring, which is less energy. So a good way to describe it is it takes less energy to sit in this inner ring than it does the outer ring. And Electrons are lazy. Everything. Atoms are lazy in chemistry. Everything's lazy. And they want to do whatever requires the least energy. So they want to sit in the middle as possible. So that's why you don't find electrons just in far off rings in the fifth outside ring. They're all shuffled into the middle because it requires the least energy. Let's think about relative masses. Your protons and your neutrons, which are in our nucleus in the middle, have a relative mass of 1. And electrons are really, really small. They have a relative mass of 0.0005. We can essentially think of it as 0. We can ignore that, and for GCSE purposes, we will say that it is a mass of 0. And then think about relative charges. Protons are +1, they are positive. Electrons are -1, they are negative. And then think about the fact that they're equal. It's +1 and -1, that's equal. And then think about atoms. They want to be stable. They want no charge, they don't want any funny business. They want just neutral, nice atoms. And because protons and electrons have the same charge in a way, +1 and -1, atoms have an equal number of protons and and electrons even. I've tried a little diagram at the bottom here to suggest that if you're balancing them on a scale of charge, this is not mass, of charge, they would be equal. If you have a look at this diagram to give you an understanding of how empty atoms are, if you put a garden pea in the middle of an American football field, or I imagine a normal football field or a rugby field would be just fine, that would be the size of the nucleus in comparison to the atom as a whole. The electrons would be on the outside of the stadium and impossibly small. You would not be able to see them with your own eyes. You'd probably need a microscope. So essentially, the whole atom is just empty space. Now let's look at atomic number, mass number. The mass number is the total mass of an atom. So if we go back here and we have a look at our masses, protons and neutrons have a mass of 1 and electrons are 0. So if you just add the neutrons and protons together, you get your mass number, sometimes called atomic mass. But if you just look for the word mass, should be fine. Then atomic number is the total number of protons in an atom. So it's also sometimes called proton number. Here's an example. Here is a carbon atom. We've used the letter symbol C for carbon. That's how we would describe that. And it's got a mass number of 12 and an atomic number of 6. So that means it has 6 protons and 12 neutrons and protons. Now think about, why is this a carbon atom? Well, the fact that it has 6 protons is the determining factor of which element it is. So for example, oxygen has 8 protons, or nitrogen has 7 protons, calcium has 20, iron has 26. That's the number of protons that has, and that determines the element. So if I decided to add a proton to this carbon atom, it would no longer be a carbon atom. It would become a nitrogen atom, and so on and so forth. Now we need to know how to calculate the number of protons, neutrons, and electrons from this information. The atomic number is the number of protons. That's nice and easy. And then remember, the protons and electrons must be equal in an atom, so it's uncharged. So we also have 6 electrons. And because the mass number is neutrons and protons, we can take away the number of protons from the mass number to find the neutrons. So 12 minus 6 makes 6 neutrons. Should be nice and easy. Isotopes. An isotope is a variation on an atom where it is the same element, hence the same number of protons, or typo, but has a different mass number, meaning it has more or less neutrons. I'll give you some examples. Here are 2 isotopes of carbon. They both have 6 protons. We have carbon-12 and carbon-13, both 6 protons, but carbon-12 has 6 neutrons and carbon-13 has 7 neutrons. Now, in reality, this has next to no effect. It would just change the weight. In chemistry, we mostly talk about charges, and neutrons don't have a charge, so this doesn't really make a difference. But you still need to know how to find this out and use this, because you'll need to calculate stuff with it later. These isotopes in carbon do not exist equally. In this example, carbon-12 is 98.9% of carbon globally, and carbon-13 is 1.1%. So they're not equal in abundance. Therefore, carbon has an average mass, which we can call relative atomic mass. And this average mass is not going to be 12, it's not going to be 13. We can, use our intuition and say it's going to be somewhere between 12 and 13. Now, to calculate this is a higher topic, so if you're not doing higher, you can skip this bit. But to calculate, we take the abundance of carbon A, for example, or atom A, which is 98.9, and then we times it by the mass, which is 12, and then do the same for carbon B, which is our carbon-13, and we get 1.1 times 13. Put that all over 100 to get it like because we've done a percentage, it is 12.011. Anyway, thank you for watching. Hope this was helpful. I have loads of other videos on all different topics in Edexcel GCSE, Edexcel GCSE, AQA, A-level, all sorts of STEM subjects, sciences, maths, DT, PE, whatnot. So go check those out on my channel. Thanks for watching.